So we have a network of capacitors here, and we're asked to find the charge on each of them. All right, so we're going to want to do what's called circuit simplification. Okay, so with this one, we want to simplify our capacitors into what are called equivalent capacitors. Now we have two ways that we can simplify. If the capacitors are in what's called parallel or series. Now let me show you an example of what parallel capacitors look like. That's an example of parallel. Why? Because current can flow through this branch, or it can take this path and still get to the opposite side. See, it's parallel. We also have series, where one capacitor is directly connected in a line with another capacitor. Okay? So in this problem, we have both parallel and series going on at the same time. So what we want to do is we want to simplify the capacitors that are in parallel. And what we'll do is we'll redraw the circuit. We'll redraw it with just one big capacitor in the place of where those other three were originally. And we leave everything else alone. So this is simplified. Now, what we can do is call this new capacitor C1, 2, 3. It's a combination of all of those, C1 and C2 and C3. And this one stays C4. All right, it's not a real capacitor. It's just an imaginary helper for us to solve the circuit. Okay. Then what we'll do is recognize that these are now in series, so we can combine them into one single capacitor. Okay. And this guy, once we get down to the very end, is called CEQ, an equivalent capacitor for the whole circuit. All right, so it's a step-by-step process. Now, first of all, we want to figure out what is the capacitance of C123. How many farads would it be? Well, C1 is 12 microfarads. C2 is 3 microfarads. And C3 is 5 microfarads. All of these present opportunities for charge to flow. Okay, so it doesn't say which side is the positive and which side's the negative here. But let's say that, this one, the top is the positive, just for the sake of drawing. Capacitors which have a smaller capacitance, they can't hold as much charge. The ones with the larger capacitances can hold much more charge. So the 12 will hold the most. Okay. We'll have an equal negative charge on the opposite sides, like that. We got to figure out how much the whole thing can hold, and I hope it makes sense just from looking at the picture that the amount that it can hold is the sum of the amounts that each of them can hold. It's almost like it doesn't even matter that they're separate entities, right? Because if you take the charge that's on C3 and put that on here, 4 pluses I put, and then 2 pluses from the 3 microfarad can go here, and then the rest of them can go here. All right, so it becomes a huge capacitor with a large capacitance. The rule for parallel capacitors is to take the original capacitances and add them. All right, so our C1, 2, 3, therefore, is going to be the 12 microfarads plus the 3 microfarads plus the 5. It's a total of 20, it looks like. All right, now when we look at our new drawing, we can put that in. Okay, and the C4 remains what it was, which was 15. Okay, so let's put that in as well. The hard part is when it comes to series. Series doesn't have a nice mathematical formula like that. It's a little bit more complicated formula. The formula is, it'll be 1 over C, I'll call it A, plus 1 over CB, plus 1 over CC. As many capacitors as you have in series, that's what you do with them. You do 1 over each of them and just add the results. So for our case, we're going to have CEQ equals 1 over C1, 2, 3 plus 1 over C4. We only have 2 capacitors in series, so that's going to be our formula here. And we just have to fill in the numbers. Our C1, 2, 3 is 20 farads, 20 microfarads. And our C4 is 15. All right, plug that into your calculator. I'm getting 8.57 microfarads. Now, interestingly, CEQ for series will always be less than any individual capacitor that we had originally. And one of the reasonings for why this is because the electrons are forced to be attracted across a gap, which could be called D, like maybe D1 here, and then they have to be attracted across another gap, D2. The larger the gap in the circuit, the less charge it can hold. That's one of the reasonings for why the equivalent capacitance is less than any one of them individually. Okay? All right, now that we have that, we have a few minutes. Hopefully we can finish this one. So we know that there's a 120 volt difference across the circuit. So that could put this point at 0 volts, and this point could be considered at 120 volts. We want to figure that this is the only circuit element involved, so we're going to have 120 volts on his positive plate and 0 volts on his negative plate. I would now use the formula for capacitance, CEQ equals Q total over delta V total. That'll allow us to find the charge on our equivalent capacitor. So I would do 8.57 microfarads equals Q total over 120 volts. So multiply those. I get 1,029 microcoulombs. So 1,029 microcoulombs here. All right. Now we would work our way backwards to figure out how much charge would be on each of the capacitors, right? But one thing's for sure. If this is your negative terminal and this is your positive terminal, then the only way that charge can flow into this circuit is onto the left plate of C4. And with that in mind, that left plate has to have negative 1029 microcoulombs on it. Because it's the only thing which can take the negative charge that's on my equivalent capacitor. Because remember, the equivalent capacitor is imaginary. We have to look back at the real circuit to see what those charges would really go on to. So it would go on to C4. That means that positive 1029 microcoulombs are going to go onto its positive plate. And those microcoulombs are going to be, they're going to be positive. So there would be an equal amount of negative charge on the other capacitors on their negative plates. All right, so we just got to work our way back, and let's look at this diagram now. We've got negative 1029 here. okay? And that means we're going to have positive 1029 here. And if we have positive 1029 there, then, oh shoot. I can't undo that, can I? All right, I can redraw it. Hold on. Anyway, I was saying we would have 1029 here, negative 1029 there. So we're going to have negative 1029 here and positive 1029 there. The reason is that this middle part is overall neutral, but it will polarize, okay, so that the charges separate. All right, so now we know that we have to have 1029 on this capacitor and 1029 on the rest as well. All right, so in order to figure out how much charge goes on each of those, you need to know the delta V of these guys, and you have to know the delta V of that guy. All right, so in order to find delta V of capacitor 4, what I would do is take his charge and also take his capacitance, and from those two things, we can now apply the rule C4 equals Q4 over delta V4. All right, we have everything we need to solve for delta V. So we'll have 15 microfarads equals 1029 microcoulombs over delta V4. All right, it's going to be 69 volts. Okay, 69 volts across that particular capacitor. Now that we know that, we've got 120 volts in the whole circuit. And you have to lose all that 120 volts. We have 51 volts dropped in that capacitor. When capacitors are in parallel, they'll lose the same amount of potential, in all of them. They'll all be 51 volt capacitors. And that's how we solve it. We know the voltage now, and we also know their capacitances. Okay, so we can apply the law to each one of them individually. So I'll do a quick calculation for C1. All right, it's going to be 12 microfarads over 51 volts. Q1 therefore will be 617 microcoulombs. You just do it for each capacitor. And I know we're running out of time. By subtracting, see, I know that this point is at 120 volts, and I know this point's at 0 volts. I said that there was 69 volts across this gap, so that puts the potential of this metal at 69 volts. And you just want to get the difference between this point and this point. And that's how much must be dropped across that capacitor. So you're going to have 20 minus 69. You get the delta V in that capacitor gap. Does that make sense? Okay. Yeah, so once you have that, the rest is just plugging them in. So 153 microcoulombs. And you just do it for C3 as well. All right, and those will be the answers to the questions.